So far, we've been focused on hypothesis testing for a single mean, where we're trying to measure some underlying but unknowable population mean by just using samples. And we might be trying to ascertain something like, what is the average birth weight or something like that. But in statistics, often we're concerned with measuring the difference between two separate populations. And that's where hypothesis testing for two means comes in. So you might want to do this whenever, let's say, you're testing the efficacy of a drug. So you want to know whether this drug is more effective than some other drug. We want to be able to compare means between the population that took the drug and the population that did not take the drug, for example. So maybe you're testing some sleep medication. In this case, you would have two separate means. You would have maybe the mean that involves sleep quality for the control group, and also a mean for the sleep quality of the group that took the drug. So this is going to be the more important type of hypothesis testing whenever it comes to experimental design. So if you want to design some experiment where you have a control group and some other population, then we want to be able to compare the results of those two populations. So, for example, let's say that you're hired to test whether Firestone tires last longer than Goodyear tires. In this case, there's not just a single population mean that we care about. We don't care about the overall average of the lifetime of tires. What we care about is the lifetime of Firestone tires versus the lifetime of Goodyear tires. So we're trying to compare two population means. We want to compare the average life of a Firestone tire to the average life of a Goodyear tire. And for this, we're going to do the same sort of strategy that we did before. So I'm going to try to measure each of these things. So I want to know what mu1 is, and I want to know what mu2 is, but I can't sample every Firestone tire or every Goodyear tire. So these are unknowable in some sense. But what we can do is what we did before, which is we can try to approximate them by just taking a big sample. So we'll take two samples. One of them will be a random sample of Firestone tire lifespans, and then X2 will be our sample for Goodyear tire lifespans. And then we'll compute the average for each of those samples. So X1 is our sample for Firestone tires, and X1 bar would be its mean. So this is the mean life of a Firestone tire, at least for our sample. And then this will be the mean life for a Goodyear tire, according to our sample. So those are going to be the two that we end up getting, the two sample means that we get. And here's how we would state our null and alternative hypotheses in these cases. So our null hypothesis is just that the actual means are equal. So remember, the null hypothesis is always stated in terms of equality. So we're just going to assume that mu1 is equal to mu2 here. And our alternative hypothesis, which we were told to test, is whether the lifetime of Firestone tires beats the lifetime of Goodyear tires. So that's our alternative hypothesis in this case. Now, we normally rewrite these so that the variable parts appear on the left side and we have a constant on the right side, like we did in the previous section. So normally I would subtract mu2 from the right-hand side of these equations or inequalities and rewrite them like this right-hand side over here. So I would rewrite that top equation as mu1 minus mu2 equals 0. And then our alternative hypothesis is that actually that quantity is bigger than 0. So let's talk about estimating this underlined quantity here. So we're going to consider the distribution of x1 bar minus x2 bar. So remember that this is our sample mean minus, our sample mean for Firestone tires minus our sample mean for Goodyear tires. And these are supposed to be approximating, so maybe I'll write it like this. Our sample means, or the difference between our sample means, is supposed to be approximating mu1 minus mu2. And remember that up here what we have is that the alternative hypothesis is that this mu1 minus mu2 is supposed to be positive. So we need to know whether that thing is positive, and we're going to estimate it by using this x1 bar minus x2 bar, because we can't know mu1 minus mu2, but we can estimate it by using our sample. Now, if the null hypothesis is true and mu1 is actually equal to mu2, then this thing should be roughly 0. In other words, if this is estimating a quantity that's exactly the same as the quantity that this is also estimating, so if x1 and x2 are clustered around the same point, then this should be distributed around 0. Now, obviously, because we're picking random samples, we're not going to get samples whose means match exactly. So sometimes I might get that x1 is a little bigger than x2, and sometimes I might get that x1 bar is a little bit smaller than x2 bar. And so we would expect that about 50% of the time we get x1s that are larger than x2 in terms of the means, and then about 50% of the time we would get x1 that's smaller than x2 in terms of the means. So maybe notice that if x1 bar is bigger than x2 bar, then you're taking a bigger number minus a smaller number. That would give you a positive number altogether. So on this region, the right side, you would have x1 bar is bigger than x2 bar. And similarly over here, if you wanted to get a negative answer out of this quantity, then you would need to be subtracting a larger number away from a smaller number. So this would mean that x1 bar is actually smaller than x2 bar. So that's how you could deviate to the right or to the left from 0. If you get 0, then that just means that those two quantities, x1 bar and x2 bar, match exactly. So here we're trying to test our hypothesis here. We're going to do the same strategy for hypothesis testing. So if we wanted to know whether x1 bar was actually bigger than x2 bar, which is what we're trying to test here, or if we rewrite it in a similar way, if I wanted to test whether x1 bar minus x2 bar is positive, if I just rewrite that equation up there, or rather inequality, then I just want to see whether I'm getting significant results to the right here. So I want to know whether x1 bar is significantly larger than x2 bar. And for that, I would need to specify some sort of a confidence or a level of significance. So I would need to know what alpha was, or that would just have to be given to you in the problem prompt. So we're not going to worry about making that too technical right now, but this is what we're looking for. We want to see whether our sample means, or rather the difference between the sample means, lives in this region over here to the far right. And if we ended up getting a difference between sample means that lives over here, we would reject the null hypothesis. But if we get one that lives closer to 0, that isn't so extreme, then we might just interpret that as being a result of chance. So maybe the null hypothesis is true and we just got sort of a random deviation, which you would sort of expect if the null hypothesis is true. So the strategy for hypothesis testing is going to be exactly the same. The only thing that's different in this section is that we're looking at this particular distribution, which is the distribution of x1 bar minus x2 bar, and that will follow a slightly different distribution. So if these are normally distributed variables, or if your sample size is sufficiently large, then this x1 bar minus x2 bar is going to be normally distributed with a mean of 0 and with this variance, assuming that the null hypothesis is true. So this is the distribution that we'll use for hypothesis testing in this section. At the end of this chapter, we'll talk about how to do this with the t-distribution, which is what you would use whenever you don't actually know these standard deviations for the whole population that you're studying. But that's sort of a general overview of what we're going to be doing here. Our hypothesis testing steps are going to be the same as before, but I thought it would be good to make a little summary video about how we're actually building this distribution from these two samples that we're making.